Okay, so we're going to be doing the data reduction for the fourth lab today for the column. I will be doing most of the data reduction, but this time you're actually going to do a few things on your own. I think it's a minimum of 2 things, and that's finding the critical stress for intermediate and long columns on your own. So for that, you have the equation from the lecture notes, so you just need to implement that equation within the for loop that we're going to construct. So, we're going to be using a for loop for most of our code in this video, and you're just going to have to put in 2 lines on your own for the critical stress for the intermediate and the long columns. All right, and you'll get an idea of what your graph should look like. It's not going to look the exact same as mine, because for this video I'm using the what is it? I think it's, let me check. I forget which group I'm using their data. Okay, it's the Pinpin group from Thursday. I'm using their data because they have it formatted very nice where they have the peak load for all 12 columns. Now, I didn't tell you guys to actually write that down in the Excel sheet, so, not your fault or anything, but it's very convenient that they did that because what I'll be doing is going through all of the different 12 data sets for the other groups and getting the max load. So I'll probably, you could do it by manually, just looking at it yourself, but, we want to learn things, right? So we can use a for loop in MATLAB to actually loop through each of those different text files, and then tell MATLAB to find the max load in each file. But I actually need to work on that because it's a little weird for how you do it. So anyways, I'm going to do that at some other point. Okay, so yeah, so the fixed pin graph for Thursday, it'll look like what I have here, or it should. But the other graphs for fix and Pinpin, they're going to look a bit different because I'm using different data. This is data from, I don't know, a few years ago and from a different class too. So it's not great results, to be honest. So hopefully the results that you guys have in this semester is better. And usually there's a bad error because those fixed supports that we have, if they get damaged, it's going to offset the way that the load is being applied. It won't be, in compression entirely. It might be kind of offset, kind of at an angle. I should say it won't be in axial compression entirely. It might be a little offset. So there might be some like shear stress going on too. So anyways, once it's crooked like that, then the test doesn't work as well. So yeah, so again, hopefully this semester was better. Alright, so all I've done here is I first loaded in the data. So actually, let me show you what that looks like too. Where did I put it? I think yeah, right here. Okay, so this data, it has 3 different sheets. So one for fix pin, one for Pinpin, and one for fix. So we have the length of the column, the actual length of the column, inside diameter, outside diameter, and then the peak load. So the critical load that we have for each setup here. Alright, so you might want to format your Excel sheet kind of like that. Okay, and then the next thing I did, I defined the elastic modulus that we have for aluminum 6061T6. And then I defined a little string array here for the effective length constant that we have. So for Pinpin, that's just the length of the Pinpin column. Making sure it's recording. For Pinfix, we have 0.7 times the length of the column. Then for fix, it's 0.5 times the length of the column. And we're going to be using this in our loop later on when we calculate the effective or the slenderness ratio. Actually, really first, when we first calculate the effective length, and then we're going to use that to calculate the slenderness ratio. So by having this kind of setup and this vector here, we can loop through for 1, 2, and 3. And then this string array, did I already mention this? My mind is gone. We have the string array, so later on we can actually loop through this vector as well when we make our plots. So for the first pass, we're going to make our Pinpin plot, second pass, Pinfix, and third, fix. Alright, and now we're going to get started on the loop. Let me zoom in so you can read everything. Okay, so let's loop for things. Not a great comment, to be honest. So we're going to do for n equals 1 to 3, because we have 3 different test setups for the different n supports that we have. And now we want to import our data. So I'll call this data. We'll do read matrix. File name, which we defined up here. File name is really just where that file is located. And then we have sheet. We want to iterate for the 3 different sheets that we have. So we'll put comma n. And then we're going to specify the range of data that we have. So it should be A2 to D13. Double check that it's the same on your Excel sheet. So you want to open this up and you're going to look where your data is, your numeric data. So for me, it's A2 right here to D13. Okay, there we go. And now we can have our data be imported. So let's run our script now. And then in the command window, I'm going to say open data. And then here we go. This is the data. I've had some questions on why it only shows like one output for a lot of the things that we calculate in the for loop. That's because we aren't telling MATLAB to store everything. We could store everything here in like a cell array or a multi-dimensional array for all of the 3 tests, but it's not necessary, so we don't need to do it. I can unsuppress this line here, and then you'll see all of the 3 different data sheets show up in the command window. So let's scroll up. Here's the first one, here's the second, and then here's the third. If you don't like how it's formatted like this, which I personally don't, you can fix that. So you're going to do format short G. I'm not sure if there's a space or not. Okay, yeah, there's not. And there you go. Now it looks better. Okay, so we have all of our data. And now we can calculate the cross-sectional area. So that's going to change. We have 3 different test setups for the different end supports. And for each test setup, we have 12 different rods. So we need to keep that in mind, right? One group on Thursday, they couldn't do the shortest rod. So we'll have to talk about that. Basically, you'll need to like put in a little filler. So you can say, for that one, kind of pretend that you had that 1-inch rod, but instead of having a number, we're going to put NaN. So not a number, and then that'll allow us to still make our plots. So anyways, here we go with the cross-sectional area. We got to calculate it for those 3 different test setups, and then all of the different 12 rods. So we're going to do pi divided by 4, multiplied by the outer diameter squared minus the inner diameter squared. So we're going to get it from our data that we imported. All of the columns all of the rows in the 3rd column. Let's square that. And then we're going to do minus data, all of the rows in the 2nd column, and then squared. All right. Oops. Like that. There we go. And let's double check that we're actually getting the right columns here. So our 3rd column is the outer, 2nd is the inner, so we're good. Okay, there's a cross-sectional area. Also, we need these little dots or periods before the exponentiation, because we are raising a vector to the power of 2, and we want to do it element by element. So, a little refresher for MATLAB. If you need to do an element by element operation, you need to signify that by this period before whatever operation you're doing. Okay, so we have the cross-sectional area. Now let's do the effective length. Okay, the effective length is going to be the effective length constant up here multiplied by the actual length of the column. So we want to do that for all 3 of our test setups here. So we'll do effective length for constant up here. And if I just type this in right now and I run our script, we have our 3 passes here. but for each pass, it's outputting that entire vector, which is not what we want. We want to have our first pass do it for Pinpin, so 1. Our second pass do it for Pinfix, 0.7. And our third pass do it only for 0.5 for fix. So we actually need to put n in parentheses here. And now if we run it, it's just like we want. Okay, so there we go. And then we're going to multiply this by the length, the actual length of each column. So data, all of the rows in the first column. Double check it again. Yeah, length. And now we will run this, and I don't need to put a period before this multiplication sign because we're multiplying a constant by a vector. So it's implied element by element multiplication here, or it's implicit. Okay, let's run this, and then we'll see it for all of our 3 different test setups. So we have our first one for Pinpin, and again, that's just the actual length of the column. So I keep opening up this Excel sheet. But let's take a look at that. So here you can see that it's all of these numbers are the same as we have over here because the effective length constant for a Pinpin column is just 1. So we're doing 1 multiplied by the actual length. Okay, for fixed pin, it's 0.7 times the length of the column. So now, oops. Oh, I had my Excel sheet messed up. I'm glad I just saw this. Pinpin should be my first sheet down here. Then fix pin, then fix. So let's save this. Yeah. Okay. So now let's rerun our script now. Okay. Alright, so this is Pinpin, yep. And all of these are the same. Then we'll go to fix pin. And again, that's 0.7 multiplied by the actual length of the column. And you see now our values are different. Did I scroll too much? Yeah, okay. Let's see. Okay, here we are. Alright, I saw a value higher than 12 and I was really confused for a second. So this is our first one. Yeah. Okay, and then we go right here. Alright, so you see that they're different. And then we go to our fix one down here. That's 0.5 multiplied by the actual length of the column. And you see that's what we have. Okay. Effective length, done. Now we gotta do the radius of gyration. So remember that this is a geometric property. So it's 1 divided by 4 multiplied by the square root of the outer diameter squared plus the inner diameter squared. I actually made a video before this and I typed in the radius of gyration incorrectly, so I think I did a minus sign instead of a plus sign. So let me double check this formula. So yeah, the 1 divided by 4 multiplied by the square root of the outer diameter squared plus the inner diameter squared. Okay, so that's k, 1 divided by 4, multiplied by the square root of the outer diameter. That's our third column. It's a vector, so we need to do element by element exponentiation. Can hardly say that word. Plus all of the rows in the second column. Raise it to the power of 2, element by element. And there's our parentheses for the square root. Run it. There we go. Cool. Now we can calculate the slenderness ratio. So we'll call that SR. And remember, that's the effective length divided by the radius of gyration. So again, this is a geometric ratio here. And if you forgot, hopefully you didn't, but this is to quantify if we have a short column, a long column, or an intermediate column. I don't know why I set that out of order. So we have 2 different vectors. We have LE and we have K. We'll just look at LE first, which we already did, the effective length, so they're all vectors. And then we have K. Those are all vectors as well. So I want to divide each element in those vectors, with each other. So the first element in the effective length, divide that by the first element and the radius of gyration. So we need to do element by element division here. So LE divided by K. Now we have the slenderness ratio. Okay, and now we are going to do, we're going to find the indices. So the rows when we have a certain slenderness ratio value. So at this point, we can actually do this a little bit differently, but I think just finding the indices first, or the rows first, it helps you just get a better idea of what we're doing. It's more clear this way. So find indices for different slenderness ratio. So what I mean is for our first test, like for Pinpin, when we calculate that slenderness ratio, we want MATLAB to just automatically say, okay, rows, maybe 1, 2, 3, and 4 are short columns. And so we want MATLAB to identify that. And then we also want MATLAB to identify the intermediate columns. The rows for intermediate columns, and then the rows for long columns. So we'll type it out, and then I'll show you what it looks like so you can actually visually confirm that what we did is correct. So short ind for indices, we're going to use the find function. So find when SR, our slenderness ratio, is less than 49.67. Okay, remember that's for a short column. And actually, I won't suppress it right now. So let's run this. Okay, and we have our 3 different outputs here. So our first one, this is for Pinpin, remember? So this is saying that the first 3 rows for our Pinpin setup, that those were short columns. So I actually want to unsuppress this as well. You know what we'll do? We'll do yeah, dummy. Okay, so what I've done now, just to make this a bit more clear, just so we can kind of compare things visually a bit better, I've made a multi-dimensional array here for the slenderness ratio calculation. So we're going to change that in the end. We don't need this, but again, it's just easier to see all of these at once. So what I did here is basically I want to get all of the rows. I could have put a colon here as well, but we just have one column. And then we're doing it for n test setups that we have. So this is for Pinpin, this is fix pin, and this is fix fix. So going back to the indices here, if we look at this, you know what, let's rename this because we're getting an issue right now. Okay, we'll leave that as SR. Delete that SR multi. Okay. Open SR multi. There we go. So for our first one here, this is for Pinpin, remember. So this is saying that the first 3 rows for the Pinpin column are short columns. So what do we do to verify that? We look at the slenderness ratio. And these are the first 3 rows here. And you see that they're all under 49.67. So they are short columns. Next one is we're still looking at short columns, but for fix pin, this is saying the first 5 rows are intermediate columns. So 1, 2, 3, 4, 5. Yep, all of those are under 49.67. Then we'll check for fix fix. That says 1 to 7. 1, 2, 3, 4, 5, 6, 7. Those first 7 rows are short columns because they are under 49.67. Okay, cool. So there's the indices for our short columns. Now let's do it for intermediate and long. I'll call this end for intermediate. Find when the slenderness ratio is now greater than 49.67 and when the slenderness ratio is less than 63. Alright, now let's look at this. So for the first one, it just says row 4. So we're greater than 49.67, but we're less than 63. So that's correct. It's only this one. For your fixed pin, it's our 6th row. So 1, 2, 3, 4, 5, 6. That's also looking good. And then our last one, fix. Rows 8 and 9. So 1, 2, 3, 4, 5, 6, 7, 8, and 9. That's looking good as well. Okay. And then obviously, now for the long columns, it's just going to be, you know, the leftovers. But we're actually still going to type out a formula or some code here. So find when SR is greater than 63. So this one is from 5 to 12. So 1, 2, 3, 4, 5. That's greater than 63, and we're going all the way to 12. Good. This is from 7 to 12. 1, 2, 3, 4, 5, 6, 7. That's looking good. And then the last one, 10 to 12 for fix. So 10, 11, 12. That's good as well. Okay. And in this one, by the way, you know, fix only has 3 of them because our effective length is shorter because we're doing 0.5 times the length of the actual rod. So because of that, you know, our values for the slenderness ratio overall are going to be smaller than fixed pin and Pinpin. Okay, so we have all of those indices, and now we can actually start calculating the critical stress for these different columns, whether it's short, intermediate, or long. So the first one, let's do it for the short columns. Critical stress short columns. Okay, so we're going to do, not that. We're going to do, I'll actually just type it out. Critical. No, I don't want to. Crit. Short. Okay. We'll do critical underscore short. Okay, there we go. So critical stress for short columns. And remember, that's simply equal to the yield stress for this, and it's 39,177. If you look this up on Google, you might get different values, but it's always around this. And I believe a few years ago, we actually given a piece of paper from the manufacturer for the yield stress for the particular columns that we have. So we're going to use this value. Okay, but here's a little issue here. We only have a scalar. And as we were just saying, you know, we have for Pinpin, there's 3 columns that are short columns. For fixed pin, there's 5 columns. And then for fix, there's 7 of them. So we need this to actually be a vector, right? Because if it's a scalar, once we make our plot, it's not going to look right. So we actually need data points for all of these values. So we need data points for 3 here, 5 here, and 7 here. So we don't want critical short to be a scalar. We want it to be a vector. So we're going to update this to now be a vector. So we're going to use the linspace command. The first argument is our starting value. So that's just critical short. And then the second argument is the ending value. And again, it's going to be critical short because we just want a vector of 39,177. So we're going to type in critical short again. And then the last argument is the amount that we want, the amount of data points. So here we're going to type in length of short. You just type there. Length of short IND. So that's going to calculate the length of the vector that we had for these indices. So basically what we're going to get when we run our code now is we're going to have a vector For Pinpin here, we're going to have 3 values that are 39,177 because we have 3 short columns for Pinpin. For FixPin, we're going to have 5 values of 39,177. For FixFix, we're going to have 7 values of 39,177. So we run it, and there we go. So this is for FixFix, so we have 7 values like we said we should have. For intermediate, or sorry, for FixPin, we have 5 values, and we needed 5. And then for Pinpin, we have 3 values, we needed 3, so it's looking good. So let me suppress both of those. And now we're at the part where you need to actually figure out how to implement the critical stress for intermediate columns and long columns on your own. So critical stress, intermediate columns, critical stress, long columns. Okay, on your own. Okay, and let me tell you, it's not as complicated as this. You don't need to use the linspace command when you calculate these. So you're just going to be using the equation, again, that's in the deliverables handout. So for the theoretical calculation for intermediate columns, we have this right here. So 38,300 minus 202 multiplied by the slenderness ratio. And you have that right now. You have that for each test setup. You have it for Pinpin, you have it for Pinfix, and you have it for FixFix. And then same thing for the long columns. You got to use this Euler buckling equation, and it's just pi squared multiplied by the elastic modulus divided by the slenderness ratio squared. And again, you have that slenderness ratio value. So you're going to be using these formulas, and you're going to implement that in MATLAB, and then you can find them. So I'm going to skip over this part because I don't want you to see it. It's simple though, okay? Again, it's not this complicated. You're just using that equation. Type it out in MATLAB. There you go. That's it. So I'm going to skip past this part, so I'm going to type it out myself, and then you'll see what it should look like. Okay, so I want to go over one more thing before we move on here. It'll be a bit of a hint of what to do. So again, you're using that equation that we talked about, or there's 2 equations, and you're going to use that, and then you can solve for them. But you need to make sure that you're using the intermediate equation for only intermediate columns, and you're using the long equation for only long columns. So you need to use array addressing. So for an example, let's go back to the indices that we found for short columns. Currently, this is for the very last loop, or pass in our loop, so this is for FixFix. So if we look over here again, that's saying that columns 1 through 7 were short columns. So 1, 2, 3, 4, 5, 6, 7, and that's what we see. So if I wanted to do something for only short columns here, I need to use array addressing. So let's say I was going to get all of these values here and multiply them by 2. But I only wanted to multiply these the values for short columns by 2. So I would only want to multiply the first 7 rows by 2. So if I do SR multiplied by 2, well, that's going to do it for every single row in here. That's not what we want. So what I need to do is SR, and then use array addressing, short IND. That's why we found those indices, and then we can multiply them by 2. And now it's only going to do this for the first 7 rows. So you see 1, 2, 3, 4, 5, 6, 7. And you can look and you can see that, yeah, it's all of these first 7 rows multiplied by 2. Alright, so that's your hint. You need to use array addressing with those formulas that we have. Okay, if you can't get it, keep trying. Number 1, I'm sure you can get it. Again, it's simple, so don't overthink it. But if you really put in effort, right, and you just can't figure it out, then you can reach out and I can help you. But you can do it. Okay, next thing is the experimental critical stress. And this is just going to be the load, the critical load that we have divided by the cross-sectional area. So we have data, all of the rows in the fourth column. Yep. And then we're going to do divided by the cross-sectional area divided by A. And A is a scalar, so we don't need to do element by element division. It's implicit element by element division. There we go. Let's open that up. Experimental critical stress. Okay, I lied. A is a vector, so I don't know what I was thinking. We do need to do element by element division. Maybe my brain was subconsciously telling me that. You see here we get a matrix. We don't want that. So do element by element division, and there we go. Now it's correct. Alright. We on plotting now? Yeah. So now we can actually make our plots. So we're going to call this fig is equal to figure of n. I was going to have you do this part. Maybe I still could. I could blur this out. No, I won't, because I'm going to show you one part, and it's the same thing for the intermediate and long columns, so whatever. Okay, so I'm going to do fig.position equals 0, 0, 750, 500. First two values are where the figure shows up in the bottom left. It's relative to that corner, so 0, 0 means it'll show up down here. And we have 750 by 500 for the plot. Fig.visible, we'll set this equal to on for now. And then we can actually make our plot. So we're gonna do it for the short columns first. Short columns. Theoretical. So we're gonna do plot SR, short IND, and then critical short. Didn't I call this? I can't really scroll because I don't want to show you my script. Yeah, critical short. By the way, yeah, you can type who's to see all of your variables that you had. Okay, so we have our slenderness ratio here. This is for the short columns. See, we're using array addressing. And then we have, well, we calculated the critical stress for short columns, and we use the linspace command to have a vector for each test setup. And we'll make this red data points, red circles. We'll do a dotted line too, and we'll change the line width to 2. That's good. We're going to type hold on, because we want to plot these here. To change these, we have enter, not enter, we have enter, and then long. And we have critical, enter, and then critical long. Make sure it's actually right, enter, okay. Critical int, I'm not really consistent here, huh? Okay, and then we're going to change these, make this blue, we'll make this green. We'll run it, and we'll get our 3 plots. So there's number 1, I think. I don't know for sure, because it's not labeled. We'll do that in a bit. I think that's right, that we have 1, 2, and then 3. Okay. Alright, so there are the plots. Oh, we need to do the experimental. So let's call this intermediate. Let's be a little more organized. Long. Now we gotta do experimental. Okay, so plot. Now we're just gonna plot the entire slenderness ratio because we're plotting all of the data points here. And here I'm gonna type in. Oh yeah, geez, sorry. I guess I just all of a sudden started blinking. We're not doing experimental quite yet. We're going to be doing this for the entire range for the theoretical stuff. Theoretical dotted line. Because, you know, right now, when we plotted this, they were actually just data points. So they do have their own plotted line, but it's only for their kind of range of data. So we want to have we're going to do a black dashed line that's going to cover this entire range here. Okay, so that's what we're doing right here. So SR, and we need to make the y argument a vector. So we need to have the short columns, the intermediate, and the long columns. So to do that, we're going to make a vector. So that's why we have the square brackets. So critical short, and then critical int, and then critical long. And again, we're going to make this a black dashed line. We'll do a line width of 2. Now we run this, and we get an error. Yeah. It's because the dimensions are wrong. Okay, we're going to append it like column vector. Damn it. It's still wrong. So, yeah, so I forgot something. Let's see where it is up here. I'll explain it in a sec. Okay. The critical short columns, or the critical stress for short columns, we need to transpose that. So, let's comment that out for now. Okay. So I'll show you what I mean. If I type in critical short, let's do size, critical short. You see that's a 1x7, so that's 1 row, 7 columns. We'll do size of critical int, and then also the size of critical long. These are column vectors. So we have a 1x7 row vector, and then we have a 2x1 column vector, and then a 3x1 column vector. And I was telling MATLAB in the beginning, I was saying I had commas here, so I was implying that we were going to make a row vector. So we have this 1x7 row vector, but we can't do this right now. We can't append these other 2 vectors here, because they're column vectors. They're a different dimension. So what I'm going to do is just transpose critical short here. And then we can append, so this is going to be transposed to a column vector. And then we're appending to that these other column vectors. And now this should work. But it doesn't, because what the fuck am I doing? Okay, critical short transposed. Yeah, it's fine. Oh, it's because I didn't put a semicolon. There we go. Okay, and now you see that we have, so that's just a little mistyping there. Now we have that black dashed line that we wanted. Okay, now we need the experimental critical stress. Oh man, I'm gonna have to blur that out. I had the code there. Okay, so we're going to do plot SR, the slenderness ratio, and now we're just going to type in experimental critical stress. Is that what I called it? Maybe not. Okay, I did. Okay, and we're going to make this one, what did I make it? Okay, I made this a solid black line. Oh, maybe that's not the best choice. We'll make this a line width of 2. And then, so we're done plotting our curves now. So we can type in hold off. Yeah, it's okay. So you see for these, the ones that have a fixed support, they're pretty bad. So there's a lot of error there. Yeah, we're trying to, a fixed pin from you guys, right? That's this one, I think. So it's still not great. Let's actually make this let's put our data markers down here. So that's Pinpin. This is fix pin or pin fix, whatever. And yeah, this value here is not great. But like we kind of talked about in the lab, the theoretical value for short columns is not great because it's constant. And as we increase the length of the column, then the slenderness ratio, that's going to increase, meaning that this is going to fail earlier. So it's going to fail at a lower critical load or critical stress. And here it's showing that it's constant, which again really isn't the case. Alright, so yeah, just stuff to talk about in the report. And also the end fixtures, if it's crooked or if they're damaged a bit, it doesn't give you good results. Okay, so we have all the plots now. Let's put in a title. It's going to be called critical stress versus slenderness ratio. Comma. And we're going to say num to string. And now we're going to put in that string array that we made earlier on. Then we're going to do dot .png. No, not dot .png. We're not exporting yet. Okay. Yeah, this looks good. Let me go on to the X label. Or I guess the legend. So we need to type this in the order that we plotted everything. So we have the short columns, we have intermediate, and we have long. And then I'm going to say theoretical. You'll see what this looks like in a bit. Theoretical. And then we have experimental. And now we can do our X label and Y label. X label, slenderness ratio, Y label, if I can type. Slenderness, there we go. Y label, this is the critical stress. PSI. AX equals GCA to get our axis properties. AX dot Y axis dot exponent. We're going to set that equal to 0 so we don't have the exponents. Let's run it now. Here we go. Okay, so Pinpin, this is what it's going to look like. So it's not too bad. Now in the beginning, this is where we have the most error, especially right here. And this one is also failing too early, so this is the experimental value, but you would expect, because this is a shorter column here, that it should have a higher critical stress than this one here. And this one. Okay, this one is for pin fix. So, yeah, not great, right? Not that you guys did anything bad again, it's a lot of it is this just sucks, the theoretical approximation there. But also this was like a really low slenderness ratio here. Not really. Not only that, just the critical stress is pretty low. Okay, anyways, I'm kind of just talking out loud here. This one, same kind of thing, and this is pretty bad error throughout, so again, hopefully you guys don't have as bad of error, but historically, like I say, for a lot of labs, unfortunately, there's a lot of error, and that, I mean, I guess it's subject to a lot of error because of things like, you know, just for this stuff, you know, if those end supports are even a little damaged, it's going to throw stuff off. Okay, so there we go. And then we're going to export the figures. So actually, let's constrain our graph so we don't have this white space. So to do that, we're going to use the xlim command. So we'll type in, do it down here, xlim. The first one is going to be the minimum value that we want. So let's do min Let's do it for our experimental critical stress. And then the max value is going to be max, not man, max. Experimental critical stress. Yeah. I guess I can't think straight. Why? I don't know why I did experimental critical stress. We need it for the slenderness ratio, you dummy. SR. SR. There you go. It's the x-axis. Come on. And there you go. Now it's looking good. Nice and constrained. Last thing, exporting the graphics. Export graphics. Need that like that. I'll just call this. We'll go in the figures folder. I'll make another folder called video figs. And crit stress VSR underscore. I'm gonna have that there. Num2 string n. And there we go. It might not run because I need to create. Yeah, I need to create that folder. What did I call it? Video figs. Alright, and now it's going to save it because I made the folder. Let's go there, and there are our figures. Okay, so that's it. Yep, goodbye.